Today we're going to be looking at some advanced topics in Newton's three laws and forces. In particular, what we're going to look at is how do we analyze and practice using forces at an angle, and then we're going to take that one step further and look at the forces on an inclined plane. First off, anytime we have forces at an angle, and this is true with forces and velocities, fields, anytime we have a vector at an angle, probably one of the most important things that you should immediately do is realize that those vectors, forces, velocities, accelerations, fields, whatever it is, have components on a horizontal axis and a vertical axis, or x and y, okay, two perpendicular axes. Okay, frequently one or both of those axes should be in equilibrium, and that's going to really help us because when that axis is in equilibrium, the acceleration is going to be zero along that axis. It may not be zero on both of them, and in more complicated scenarios, it's zero in neither. But having that zero really simplifies things. So, for example, here I have two sets of forces are pulling on a barge as shown, okay? We have a mass of the barge, we have angles, and we have forces associated with the horses, or the two forces pulling the barge, okay? It says ignore water resistance at this point, so again, simplifies the problem. All I have are two forces that I really need to focus on, okay? But I do have two forces at an angle, so I have to resolve both of them into their individual components. Okay, based off of the trigonometry, we know that the x component of force 1 gets multiplied by the cosine of 30, and the y component gets multiplied by the sine of 30, or 45 for the second. Okay, when you go through the math, you find the various components are listed here. Okay. It's also important to remember that F2, okay, F2 is in the fourth quadrant. Okay, you'll have to do this anytime it's not in the first quadrant. I notice that I use for all my angles, I use the absolute value of that angle, okay? Absolute value with respect to the horizontal axis, or the x-axis in this case. Okay, it's 30 degrees. Even if it was in the second quadrant, I'm still going to measure that angle to the x-axis, not all to the closest x-axis, or the negative x-axis if it's in quadrant 2 or 3. Okay, so you need to remember to adjust those components for the appropriate quadrant. In the fourth quadrant, as F2 is, okay, in that fourth quadrant, the y component will be negative. X component is positive, but the y component needs to be adjusted to minus 422 newtons. Okay, now that I have the various components as shown on the right here, okay, Newton's second law comes into play that says the acceleration is equal to the sum of all those forces divided by the mass. Okay, because of the way we treat vectors, I can basically just limit it to the x-axis and the y-axis. I don't need to go into I hat, j hat terminology, though we could do that if you find that easier. Okay, but the sum of all the forces in the x direction, just add them up. Same with the sum of the forces in the y direction, just add them up. Pay attention and for those minus signs though, okay? Because it's not 298.5 plus 422 newtons. It's adding the minus 422 newtons because it's in the negative y direction. If I do that and divide by the mass of the barge, okay, the mass of the barge is 1,330 kilograms, okay, I find that my acceleration in the x direction is 0.71 meters per second squared, and the acceleration in the y direction is minus 0.093 meters per second squared. If I wanted the total magnitude, I'd have to use the Pythagorean theorem, add the square of those things and square root. Okay, but I was just interested in finding the acceleration. I could write it as 0.71 I hat minus 0.093 j hat. Okay, I know I have some acceleration in the x, and because of the angles, it's actually going to, my barge is actually going to accelerate in the y direction as well. Okay. Always check for additional info given in the problem. Okay, see if you know anything additional. Okay, in particular, the object is frequently in equilibrium on one of those axes. Okay, meaning you can set acceleration on that axis equal to 0. As long as the acceleration is equal to 0, the forces along that axis must balance. Okay, and in the worst case scenarios, you may need to solve a system of equations. Okay, you can't just look for numbers and work in a straight line fashion. Okay, there can be a system of equations involved. So that brings us to inclined planes. Okay, in the inclined plane situation, we draw the same free body diagram. We have gravity going straight downwards. We have the normal force going perpendicular to the surface. Frequently there's going to be friction, and that's going to be parallel to the surface. The acceleration of the block is limited to the plane of the surface. Okay, so here's my free body diagram for a block on a plane. Okay, look and see there are two different forces at an angle, and the net force, or the acceleration vector, is also at an angle. So if I do that, I've got to deal with a lot of things breaking into components. The normal force breaks into a component, friction breaks into a component, and more importantly, acceleration will have an x and a y component. There's no zero associated with that. So we have a mathematical trick. That's all it is. It basically takes your x and y axis and rotates it to match the direction of acceleration. The reason we do that is to make one of the axes in equilibrium. In this case, the axes perpendicular to the plane, to the inclined plane. Okay, that now has become 0, and that is going to be significant in terms of simplifying my problem, because anytime we have a 0, I can say the forces in that axis must balance off. Okay, also notice that the angle that we're talking about here, okay, the angle theta that we had back here, okay, the blue theta on the lower corner, that is now the same as this angle theta. Okay, because the axis was rotated, that theta degrees, it used to be up and down, left and right, but we rotated it to match the plane, okay, because that's the direction of my acceleration. So that's the angle theta, and the components for gravity are going to be here, okay, because this is the 90-degree angle. So I don't want you to think of the components as being, well, the x component becomes sine, and the x component becomes cosine, because you have to pay attention to the trigonometry. Okay, the perpendicular component, okay, the x, the one going up and down, or mostly up and down in this case, that's the cosine, because that's the adjacent side. So cosine times the weight of the object gives me the perpendicular component. Sine times the magnitude of weight gives me the portion of gravity pulling the block down the ramp. Okay, so that's illustrated here. I don't really want you to be using x and y as your axis labels. The reason for that is because people frequently just memorize, well, cosine, that gives me the x, sine gives me the y, okay? And that can confuse people because of how they label their things, okay? Like I said when we were doing vectors, okay, it's always better if you use the trigonometry, the trigonometric definitions in terms of adjacent and opposite, sine, cosine, those definitions, okay, to calculate the various components. That's always going to be better than just memorizing the formulas. Okay, and the whole reason we do this, okay, is to get that equilibrium along the parallel axis. By doing that, you can avoid having to go through the systems of equations approach and pulling in all sorts of additional information necessary, and makes the problem much simpler, as well as only having to deal with one force that has components. Thank you.